Problem 9 gives you, says that a rectangle has dimensions L by W, length times width. And that, of course, gives it area LW. And the question is, if the length increases by 2% and the width increases by 1%, by what percent does the area increase? Well, if the length increases by 2%, then new length equals old length plus 2% of the old length. So length is length plus, and that should read 2%. Let me fix that. Okay, now it reads length plus 2% of the length, which is the length plus 0.02 times the length, which is a length times 1 plus 0.02, which of course can then be written as 1.02 L. This is a factoring here. We factor L out of both of these terms, and we confirm that this works by doing the distributive law here directly. L times 1 is L, L times 0.02 is 0.02 L. Magically, we did factor this correctly, and of course 1 plus 0.02 is 1.02. Now if we increase the width by 1%, our new width is 1.01 W. So that our new area is going to be new length times new width, 1.02 L times 1.01 W. Now you could put that into a calculator and get 1.0302 LW directly. Why would we go to the trouble of expanding this? Because it teaches us something, and you don't teach yourself anything by using a calculator. Naturally, if it was 1.027835 and 1.015863, it would be appropriate to use your calculator if you needed a precise result. But here, it's not appropriate for understanding what happens to this area and the percent change in the area. So we break the 1.02 and the 1.01 back down into 1 plus 0.02 and 1 plus 0.01. And then we multiply these as binomials, not using that F word thing, that FOIL thing, but using the distributive law, which is what we need to understand. 1 times 1 plus 0.01 plus 0.02 times 1 plus 0.01. Okay? Now 1 times 1 plus 0.01 is 1 times 1 plus 1 times 0.01, which gives us 1 plus 0.01. 0.02 multiplied by 1 plus 0.01 gives us 0.02 times 1, which is 0.02. 0.02 times 0.01, 0.02 times 0.01. And now we add these, the 0.01 and 0.02 up, and this is very important to remember that that's what we did with these numbers and how they're related to the numbers we started with. And we get 0.03. And now we've got three numbers. We've got the 1, which is going to be 1 times LW, which is our original area, plus 0.03 times LW. That's 3% more than the original area, or that's 3% of the original area. So when we do 1 plus 0.03 times LW, we've increased the area by 3%. Remember that 3% came from adding the 1% and 2% and how that came out of here, and everything else we've done. And then we got this tiny number, 0.0002 times LW, that really doesn't amount to a hill of beans, but we're going to include it in the calculation for the moment. And we're going to say, well, okay, that's 1.0302 LW. Now you have a connection to where the 0.03 came from and how it's related to the 2% and the 1%. And you have that 0.02 there. You see where that came from, multiplying this by this. And you notice that this is much smaller than this. The 0.0002 is much smaller than the 0.03. And then we round this off on the premise that the 0.02 ain't worth a hill of beans. It doesn't make much difference. Now, if we want to get a really precise result, we do want to include the 0.02, but for many practical purposes, that 0.02 is irrelevant. And we come to the conclusion that our area is very close to 1.03 LW and that our area has increased by 3% as a result of a 2% increase in length and a 1% increase in width. So to get the increase in area, the percent increase, it's 3.02%, but that's very near 3%. And we conclude that a 2% change in L and a 1% change in W gives us a 1% plus 2% equals 3 plus 3% change in LW. And then we conjecture, well, to get the percent change in the product of two numbers, due to small percent changes in those numbers, like the 1% and the 2%, all we got to do is add the percent changes. Now, if you can prove that 1 plus A times 1 plus B is very close to 1 plus A plus B, provided A and B are both small, both much less than 1, then you have a basis for restating this in more precise mathematical terms and actually proving it. Now, that's not the kind of thing our educational system leads us to do. We're too busy teaching people tricks to beat the SOL to teach how to prove much of anything. But if you got an exceptional teacher and a class that doesn't demand all her attention or his attention for more trivial matters, you might actually have seen some of this, but I don't think that's very common. Teachers would like to do it, not their fault. Okay, well, and there's a geometric picture here. We have our original rectangle, which is in the black here, that's L by W. And then we have the expanded rectangle where we've increased the length by 2% and the width by 2%, giving us length 1.02 L, width 1.01 W. And then we've got these little strips along the edges. Okay, we got this strip here, which takes the 0.01 W that we added and puts it together with length L to get a rectangle of dimensions 0.01 W by L, with area then 0.01 LW. And this purple rectangle, which has dimension down here of 0.02 L, the amount we added to the original L to get our new length. And the other dimension is W, so that the area of this purple thing is W times 0.02 L, which is 0.02 LW. And then this little red area here. Now, let me point out that 0.02 L is much smaller than this, and 0.01 W is much smaller than the width we have indicated here. I had to draw them bigger in order to be able to see them. The actual widths would be less than the width of a chalk line, most likely. Okay, so this little rectangle, though, has dimensions 0.01 W by 0.02 L, which is 0.0002 LW. And we understand that if we had drawn these to the actual scale, this rectangle would be really, really tiny. You know, you'd be able to kind of see these strips, but that rectangle would just be a little dot up in the corner. Okay. So you should understand the connection between this picture and this algebraic expression and this simplification down here. And all that to this idea.